So next in Unit 3, we've went through gravitational fields. We're now going to look at electric fields. So this is our electric fields portion of this unit. After this, we're going to do magnetic fields. We'll start with a lecture on Coulombs Law, which is section 7.2 from your textbook. You can read through section 7.1, but no work is assigned from that section. So the bulk of the work for this unit, well, I guess the bulk of the understanding for this unit comes from this lecture, which is 7.2 in your textbook on Coulombs Law. So we'll start, and it says here that if you drop a tennis ball, the force that causes it to fall is the force of gravity. And it will, the ball will fall, it will hit the floor, and it'll bounce back. So it says here it'll take about 1 second for the tennis ball to fall from a height of 5 meters. How long do you think it will take the tennis ball to stop as it hits the ground? And it says it'll take a lot less time than it took to fall. So what force stops the tennis ball? And really, it's the repulsion of the floor that's stopping the tennis ball. And that repulsive force, that force is actually an electric force. It's the force between the protons in the tennis ball and the protons in the floor that are repelling each other. And that repulsion, that repulsive force, will cause the tennis ball to lose its kinetic energy with each bounce and then eventually stop. So if the force of gravity was stronger than the force of than the electric force, the tennis ball would be pushed down even further, and that repulsion wouldn't be strong enough to stop it. This simple little thought experiment proves that the repulsive force of electricity, or the electric force rather, is stronger than the force of gravity. So with gravity, the source object and the other object we're comparing, there's always an attractive force between them. So there is no positive gravitational force or source, and there is no negative gravitational source. There's just a gravitational source. But when we talk about electric force, we have to apply a positive or a negative aspect of that force to it. So what we have in electricity is that the like charges would repel. So a proton repels a proton, and an electron repels an electron. And the unlike charges attract. So a proton attracts an electron, and an electron attracts a proton. So that makes it a little more complex than just the gravitational force. And when I was mentioning proton and electron, it's not necessarily always a proton and an electron. You'll see when we get into this, we're going to talk about a group of charges that could be down to a single electron or a single proton, or it could be a larger value that's represented by a combination of electrons and protons. So in terms of how we determined this electric force and how we measured for its universal constant, there was a scientist named Charles Coulomb, and he took Henry Cavendish's experiment, the torsion ballast experiment that was used to calculate the big G, the universal gravitational constant, and he basically did the same experiment, and he analyzed electrostatic forces. So he had pith balls, which were spheres that could be charged, and he basically charged them positively or negatively, but the same charge, so that they would repel each other. And then he measured the deflection from the two spheres against the wire, and using this and comparing, basically he knew what the electric force was by seeing what the deflection was, He set the charges, so he knew what his Q's values were, and he set the distance. So he was able to isolate for a universal electric constant, or electrostatic constant. And this slide kind of explains a little bit more of what I just said. And by doing that, he found that the force between 2 point charges is inversely proportional to the square of the distance between the charges and directly proportional to the product of the charges. And this is what we call Coulombs Law. Now you'll notice this sounds very similar to how we define gravitational force. So with gravitational force, it's the force between two gravitational sources is inversely proportional to the square of the distance between them and directly proportional to the product of their masses. In the case of electrostatic forces, it's the force between the 2 point charges is inversely proportional to the square of the distance and directly proportional to the product of the charges rather than the product of the masses. Now, one other aspect, though, with gravitational force, we always know the direction is attractive. So they're always going towards each other. With electrostatic force, we have to consider whether both objects are the same or whether they're different, opposite. If they are opposite, they would have, the forces would be acting in, so they would be attractive. If they were the same charges, they would be repulsive, so they would be acting out. So this is Coulombs' law, and K is Coulombs constant that was measured using the torsion balance experiment, similar to the one that was done by Cavendish to find our universal gravitational constant G. Please copy this slide down. Your Fe is your electrostatic force. K is Coulomb's constant. It's a rather large number, 8.99 times 10 to the power of 9. Its units are Newton meters squared per Coulomb squared. Q is the charge of the objects, and that's the charges measured in coulombs. And R is the distance between the centers of the objects. Now, the note, which I'd like you to copy down as well, it says the value of Fe applies only to point charges. So what we're going to be looking at in this course is we're going to take a bundle of, or rather an object that has possibly a series or a different area of charges. We're going to consider it as a single point charge. So what is the average difference between its charges and concentrate it down to a single point in the center of that object? It makes the math a lot easier, and when you get into university, you'll be able to study how to do electrostatic force calculations when we are not dealing with point charges, because it gets a bit more complicated, but it's outside the scope of this course. So this first question here, it says, suppose we have two boxes of electrons. The total charge is negative 1.8 times 10 to the 8 coulombs, and it's separated by a distance of 1 meter. We're asked to determine the magnitude of the electric force between the boxes. So we're going to say these boxes are point charges, and these charges are 1.8 times 10 to the power of 8. Notice that they are negative. So this would be two like charges. And I guess we'll switch over to the paper here so that I can write this out. So the main equation for this lecture is very similar to the gravitational equation. Fe equals K Q1 Q2 over R squared. Now in our case, Q1 and Q2 are the same. So we're going to fill in our values here. This is 8.99 times 10 to the power of 9. I'm going to write this as a square, 1.8 times 10 to the power of 8. And I'm going to square that. And I'm going to divide this by the distance between them, which I think was only about was it a meter? Yeah, 1 meter squared. So that shouldn't be difficult to calculate there. Now, first thing I'll do when I calculate this, I'm going to put 8.99. I'm going to multiply that by 10 to the power of 9. And I'm going to save this into my memory because I know I'm going to need that quite regularly. So this K multiplied by 1.8 negative squared times 10 to the power of 16 and divided by 1 squared. Well, it doesn't really matter. When I write this out, I get 2.9 times 10 to the power of 26. So that value, that 2.9 times 10 to the power of 26, is extremely large. That's larger than the gravitational force between the Earth and the Sun, believe it or not. And that is just from 2 small containers of electrons. So why is it that the electric force doesn't dominate everyday life? And the answer is because we don't usually have charges that are that high. Because for every proton in the universe has an associated electron. So most of what we experience is electrically balanced. There is no displacement of, or there's no difference of charges that's going to be that great between one object and another. Although the slight differences between them do cause these charges, or these forces. So basically, because everything is nearly equal to its electrons and neutrons, even though that force that is experienced by that unbalanced electric charge is so great, we don't experience very large forces. Okay, here's a question. It says we have a small sphere carrying a charge of -8 microcoulombs. That's 10 to the negative 6. And it exerts an attractive force of 0.5 newtons on another sphere carrying a charge of 5 microcoulombs. Well, it says the magnitude of 5 microcoulombs. So we don't know whether that's positive or negative. But we have to figure out if the sign of that is positive or negative. So let's think about this. And I know the answer is there, but I'll talk you through it. It says the first charge is -8 microcoulombs, and it is attracted to another charge that is has a magnitude of 5. So the value of -8 and the value of 5 is irrelevant. The fact that it's attractive is relevant in terms of determining whether this is positive or negative. The first charge is negative. If the second charge was negative, then it would be a repulsive force. So that means the second charge has to be positive. And now we're asked to find out what's the distance of separation between the centers of these spheres. So let's answer this. It's the same equation again, but we're going to rearrange it. So I'm going to rearrange this equation to solve for r, and it's going to be the square root of k q1 q2 over fe. And that works out to the square root of 8.99 times 10 to the power of 9. So we're going to have 3 rather large values here. Just a second, I need to slide this over so I can read it. This is -8.0 times 10 to the negative 6. And the other charge is, I don't have space for it, so I'll just write it onto here. Okay, so the other charge is 5.0 times 10 to the negative 6. And this entire thing divided by 0.5. So when I calculate this, I have K times 8. That's negative. Actually, I should say this is actually we don't write this down as negative. I'm sorry, I just remembered. And the reason why is because when we're putting our Q values in here, if we put it as a negative, we will get this square root will not work. We have to recall that that negative is actually just a kind of a directional sign. So by removing it, we'll have to remember that one of these was negative, one was positive, so the force is going to be attractive for both Q forces that experience an attractive force. So our K value times 8 times 5 times 10 to the power of negative 12. I'm just going to combine those together. That entire thing divided by 0.5, and I find the square root of this. I end up with an R distance of 0.85 because I had 2 significant digits for each. Okay, another question. This one here says we have 2 charged spheres. They're 5 centimeters apart. They attract each other with a force of 24 newtons. So the fact that they're attracting each other means one has to be positive, one has to be negative. It says determine the magnitude of each charge if one sphere has 4 times the charge as the other, and it must have the opposite sign. So when they're saying magnitude here, we don't have to write one as positive, one as negative. We're just writing down the magnitude. So to solve this problem, let me just slide this over here. What we will do is we will write down our FE, which is K, Q1, Q2, over R squared. We know that one charge is 4 times the other. So we're going to, instead of writing Q1 and Q2, we're just going to write down Q for one of them. And the other we're going to write down as 4Q, because it's 4 times the magnitude. Now we're ready to solve this. And it is FE equals 8.99 times 10 to the power of 9. Q squared, or rather 4, Q squared. FE is 24. I guess I could have rearranged this first. That entire thing over R squared, which is 0.05, because it's 5 centimeters squared. Let's move this over here and solve for Q. So rearranging for Q, Q is going to be the square root of 24 times 0.050 squared, that 5 centimeters squared, divided by our K and our 4. So this works out to 24 times 0.05 squared divided by 4 divided by K, and I find the square root of that. I end up with a Q of 1.3. 10 to the negative 6 is going to be microcoulombs. And if that is my Q, that means my Q1 must be 1.3 microcoulombs, whereas my Q2 is going to be 4 times that, so I multiply that by 4. Oops. Well, it was simply 1.3 times 4, and I know the answer is already written there. It's 5.2 microcoulombs. Okay, so now we will continue with the lecture here. This slide, actually, I want you to try by yourself. So it says 2 oppositely charged objects exert a force of attraction of 8.0 newtons on each other. What will be the new force of attraction if? And then they give you different conditions. So I want you to try this out. The answers are listed. This is kind of in addition to the homework, so see if you can complete that. And then I'd like you to, I wanted to kind of point this out. I did mention it earlier. The Coulombs Law is very similar to that universal law of gravitation we have. And if we look at the two equations side by side, we can see it a lot clearer. The only real difference between these is that we have a Q on one side and an M on the other. So we have product of the charges on the left, product of the masses on the right. We have two different constants, but they are constants. So we have a K constant and we have a G constant. Other things to note is that these are non-contact forces. So to experience the force of gravity, you do not have to be touching. Two objects don't need to be touching. They experience it just by being within the same field. The forces are weaker as the distance increases because they're divided by that distance squared. They're inversely proportional to the distance squared. And they're stronger as we get closer together or we increase the mass or the charge. Some other things to note. The gravitational force is always attractive. So the electric force can either be repulsive or attractive, depending on what types of charges we have, whereas the gravitational force is always attractive. And the magnitude of the electric force is much greater than the magnitude of the gravitational force over the same distance. So this slide I'd like you to copy down. These are the similarities between the electrostatic force and the gravitational force, and some differences as well.